So, have you ever wondered how an AI goes from looking at just a mess of data to actually making smart decisions? Well, the secret is that it has its own language, a language written completely in math. And today, we're going to crack the code, demystifying the core symbols that let a machine learn, and turning these abstract equations into something we can all understand.
You really got to wrap your head around this one thing. Every single neural network, whether it's suggesting your next song or driving a car, sees the world through mathematics. And we're not just talking about some abstract stuff for a whiteboard. This is its alphabet. It's the fundamental way it reads, learns, and ultimately understands our world.
So why is this math language so critical? Well, it all comes down to how a network gets trained. We're about to pop the hood on that process and find its real secret weapon.
At its heart, training a neural network is basically a four-step dance that it does over and over. Step 1, you give it some data and it makes a guess. That's the forward pass. Step 2, you measure how badly it messed up that guess. That's called calculating the loss. Step 3, and this is the really key part, you figure out which way it was wrong. That's calculating the gradient. And finally, you tweak all its internal connections, its weights, to be a little less wrong next time. You just do this again and again and again.
Now, the engine that powers this whole training loop is an algorithm called stochastic gradient descent, or SGD for short. Its entire purpose in life is to make that error, that loss, as small as possible. It needs that gradient from step 3 to do its job, but how? What tool does it actually use to figure that out?
And that brings us to backpropagation. This right here is the star of our show today. It's the specific, incredibly efficient algorithm that SGD uses to calculate that gradient. It's the thing that tells the network exactly how to nudge every single one of its connections to get just a little bit smarter.
Okay, so we get why we need it. It's super important. But that leads to the real million-dollar question. How does it actually do it? How does backpropagation look deep inside this massive network and calculate that gradient so perfectly? Well, to answer that, we've got to learn to speak its language.
So, let's think of this next part less like a math class and more like a language course. We're about to learn the essential vocabulary, the building blocks, that will let us read the story of how a network actually learns.
Every symbol we're about to see has a very specific, very concrete meaning. Our mission here is to decode them, to translate this math into ideas we can actually picture in our heads.
All right, let's start with the absolute basics. When you see a big old capital L, that's just the total number of layers in the whole network. Simple. And a lowercase l? Think of that as our little pointer. It just tells us which specific layer we're looking at right this second. Layer 1, layer 2, layer 10, whatever.
Now things get a little more specific. We need to be able to find any single neuron or node in this whole web. Think of these next letters as a coordinate system, like a GPS. L tells us which layer we're on. Then the index J points to a specific neuron in that layer. And the index K, that points to a neuron in the layer that came right before it, layer L-1. So L, J, and K, that's our GPS for getting around the network.
And right here is where those GPS coordinates totally click. When you see a W for weight, with all those indices, W, J, K, L, that's not just any random weight. It's talking about the specific strength of the connection going from node K in the previous layer to node J in our current layer. The level of precision here is just incredible. Now, pay close attention here, because the difference is tiny, but it's a huge deal. On the left, with both J and K, we're talking about one single connection, like one wire between 2 points. But on the right, when we drop the K, WJL, now we're talking about a vector. It represents the entire bundle of all the weights feeding into that single node J. It's the difference between one wire and the whole cable.
So what happens when all those signals, each with its own weight, arrive at a neuron? They all get added up. And that raw combined input, the weighted sum before the neuron has even done anything with it, that is what ZJL represents. You can think of Z as all the raw info a neuron gets.
This slide really lays out the whole journey for us. First, the input arrives. That's our Z, the weighted sum. Then, the neuron processes it using something called an activation function, which we represent with G. And finally, it sends out its own signal, its output, which we call A for activation. So the flow is simple, from Z through G to become A.
All right, so here's a quick little cheat sheet of the key players we've just covered. We've got C0 for our loss or cost, YJ for the correct answer we're hoping for, and then the crew we just met. W for a specific weight, Z for a neuron's input, and A for its output. This is our core vocabulary right here.
Okay,
I know what you might be thinking. All these little letters, the superscripts, the subscripts, it can look kind of intimidating, a bit messy. But I want to show you why these indices are actually your best friend in this whole process.
And hey, don't just take my word for it. As our source material puts it so well, using these indices the right way is what saves us. They don't create confusion, they get rid of it. They give us the absolute clarity we need to navigate these incredibly complex systems.
Here is a fantastic way to think about it. If you've ever written a line of code, you know what a for loop is, right? It uses an index, let's call it k, to go through a list of items one by one. Well, in math, that big sigma symbol for summation does the exact same thing. The index k tells it which numbers in a long list to add up. It's the same idea. It's a tool for looping through things.
And that's why this whole thing matters so much. Backpropagation, at its core, is an iterative process. It takes a step backwards through each layer, visiting each neuron one by one. And these indices? They are the GPS coordinates that let the algorithm travel through this massive web with perfect precision, so it never, ever gets lost.
So look what we just did. We went from a bunch of what looked like confusing, random symbols to a language that gives us a crystal clear map of the entire learning process. We've built a real foundation here, turning abstract notation into actual gut-feeling intuition.
So let's just quickly recap what we've unlocked. We've seen that backpropagation is the magic behind how networks learn from their mistakes. We've learned that this math isn't something to be afraid of. It's just a super precise language. We now know that those little indices, L, J, and K, are what turn a huge, messy formula into a clear roadmap. This language isn't a barrier to keep you out, it's a tool to let you in.
By getting a handle on this notation, you're not just looking at formulas anymore. You're looking at the actual blueprint of artificial intelligence. You now have a key piece for understanding how these incredible systems really work. So I guess the only question left is, now that you can read the language, what are you going to build?